Maysaya Lex Xavier, a fifth year BS Physics studying here at UP Baguio. My thesis title is Variational Minimization of the Ground State Energy via Physics-Informed Neural Network, a case study for bulk silicon and aluminum. My thesis works generally on improving the current materials algorithms to predict how these materials behave in the atomic or molecular level. Current algorithms are now very accurate, but they can take a significant amount of time because our computers had to adjust these parameter solutions until these solutions become physically consistent or meaningful. Specifically, I am working on the potential of using deep learning on variational optimizations to solve for the Kohn-Sham equations under the density functional theory. This density functional theory, or DFT, is the most widely used theory for material study. I'm trying to see if we can integrate these Kohn-Sham equations and a deep learning framework that solves the variational optimization problem to bring about significant results while still maintaining physically consistent solutions. In this study, we've used bulk silicon and aluminum as our test materials to see the application. I'm fascinated with the potential of physics-informed deep learning. It is very interesting because we get to integrate the physical laws or governing equations that we've learned about in our undergraduate study into the machine learning applications. So upon intensive literature review, I found that the DFT or the density functional theory is a great theory or framework to apply machine learning into. That's why I'm doing this study to see whether or not the application for the deep learning, physics-informed deep learning is actually feasible and actually improves the current simulations or algorithms that we have. My thesis provides a great starting point for future researchers to scale the model for more generalizability for more complex materials. For example, by adding defects or by adding layers towards the base material. Additionally, it contributes to the emerging scientific machine learning literature that tries or attempts the integrating existing physical laws into machine learning. Definitely, the most difficult part that I encountered in doing this study is the hyperparameter tuning required after the initial training of the neural network. It is in this step where I've encountered false positives per se, wherein the machine learning model produces a set of solutions for the variational optimization but is not considered physically meaningful. Therefore, I have to tweak some parameters within the neural network or within the custom loss function to motivate the machine learning model to produce solutions that will lead to physically meaningful results. In contrast, the most fun part is the small wins that I've had when the machine learning model first produces these physically meaningful results that I've said before. These small wins or this early convergence in the neural network training and optimization motivated me to pursue this study further and to complete my manuscript at the end.